Let's go through Diffie-Hellman key exchange. RSA can be used for those 3 different security services. That is, we can use RSA for confidentiality. We can encrypt data. We encrypt with a public key of the destination, and they can decrypt with a private key. So RSA, we can encrypt data. We can use RSA for authentication by encrypting with a private key. Authentication is checking who sent the data, check they are who they say they are. So we can use RSA for that, and we can also use it for a key exchange. That is, we can send a secret encrypted using RSA. But there are other algorithms. RSA is not the only one. And some have different purposes. The one we're going to go through is Diffie-Hellman key exchange. Diffie and Hellman, the 2 guys, developed public key cryptography. So they're the guys who created it, or first publicly released algorithms for public key cryptography. The key exchange is not used for encryption. It's not used for authentication. As the name suggests, it's used for exchanging a key, a secret. The goal, I want to tell someone a secret in a public network. That is, I want to yell it out. I want them to know the secret, but no one else to know the secret. That's the goal. That both of us have some secret. Anyone who intercepted the messages will not be able to find that secret. And that's what Diffie-Hellman key exchange does. Let's go through how it works, and we'll go through with an example. So this is created by Diffie and Hellman. Not for secrecy. Again, we'll see it's based upon discrete logarithms. The security is. That is, with discrete logarithms, it's relatively easy to calculate an exponential in modular arithmetic, but it's computationally hard to do the inverse. To take a to the power of b mod n, easy, but to find what the index is, the exponent is, given the modulus and the answer, is relatively hard, the logarithm. That's what it's based upon. This is the algorithm, and we'll just demonstrate it with an example. There are some public values that are known. When we say public, it means everyone knows them. The 2 people involved and the attacker and anyone around. There's a prime number q and some alpha, which is less than q, and it's a primitive. We usually choose alpha to be a primitive root of q. We mention primitive roots in number theory. You don't really need to understand how they work and what are primitive roots. Here we just need to know it is a primitive root of q. We saw that's part of the discrete logarithm. So they are known. That is, we choose those values, q and alpha, tell everyone, write it on a website, whatever. Everyone knows those 2 values. User A generates a key, and also user B generates their own key. User A selects a private value, xa, which is less than q. Then they use an equation to calculate y, ya, which is alpha to the power of xa mod q. So that's the equation for them to generate their key. This is a public value, y. I've got no more to get you to on the board at the moment, but soon. Each user follows the same steps here. If you look at the steps for user A and user B, they are the same. Just user A chooses a value. Let's call it xa, a private value. It doesn't tell anyone that. And calculates a public value y based upon that. Where y is alpha, alpha is public, it's chosen, and alpha to the power of xa, which is the private value, mod q. Q is also public. Only secret thing there is x. B does the same. So A is on one side of the internet, B is on the other side of the internet. They both follow this process. Choose their private x, calculate y, exchange values of y. That is, I send my y value to the other person, they send me their y value. And from those received y values and the x values, calculate y to the power of x mod q to give us k, That's at user A, and user B calculates YA from user A to the power of XB mod Q, and they get the same K. The goal is that both users have the same secret value, K in this case, and that no one else can find that secret value. And if we follow these steps, we'll see that they get the same K, and we'll show why no one else can find that value of K. So let's demonstrate this with an example. And I think you have the example in front of you, do you? Is it in the lecture notes? I'm not sure if I printed it. Maybe not. No, it's on the website, so you can write it down and follow me. It's the example's on the website. So is the description of the RSA that we went through last week and finished yesterday. That detailed description that explains why RSA works and how do we get ED and N. There's a description on the website that you can download, and it includes this example we're about to go through. Is there an example on the next slide? That's the process. No. Okay. So the first thing is that we need two what's called public elements, two public values, Q and alpha. I'm going to use some small numbers so we can do the example. I choose Q to be a prime number. It needs to be a prime number, 353 in this case. And alpha less than Q, and a primitive root of Q. So you need to work out what are the primitive roots. Turns out that 3 is a primitive root of Q in this case. So these are given. In fact, in some cases that you can use the same value for alpha. That is, you can use 3. Primitive root, when we looked at, if we take some number and raise it to the power of 1, mod n, the power of 2, mod n, raise that number to the power of 3, mod n, and raise it to the power of n minus 1, mod n, all those answers will be unique, distinct. We mentioned that at the end of number theory. That is, a primitive root of some number is that it gives us distinct set of answers if we raise that number to all the possible powers in using that modular arithmetic.
We can choose any number less than 353.
As long as it's a primitive root of 353. I will not ask you to determine if it's a primitive root of 353. There's an explanation in the lecture notes, and we did go through in number theory, but that's not the objective here, to understand how to determine a primitive root. Let's say alpha is given, Q is a prime number, so as long as it's a primitive root of 353, that's okay. And these values are public. You all know them, and the two users that are going to exchange their secret key know them. So we have user A and user B. Let's say two computers or two users on either side of the internet, and they follow these steps. User A chooses a private value. Let's call it XA, X, the private value. Let's choose a large number. It needs to be less than Q in this case, so less than 353. User A chose 97 here. And they calculate their public value based upon that, YA, where the way to calculate it is take alpha raised to the power of XA mod Q. Alpha to the XA mod Q. Alpha and Q are known. 3 to the power of 97 mod 353. So this is the way that user A generates their public value YA? Do I have a calculator to answer that? It's a good question. You use your calculator to answer that. Some calculators will. Anyone got a calculator can answer that? Sometimes your calculator will not handle. Google will give the answer. 3 to the power of 97 mod 353. Give an answer. Note that because it's a mod 353, the calculation could be simplified using the expansions that we've seen before. If you calculate 3 to the power of 97 and press equals on your calculator, and then use mod, even on a computer-based calculator, and then so you do 3 to the power of 97, press equals, you get an answer, a big number, and then try mod 353, the calculator may not get an answer. Because to calculate this efficiently, you normally need to expand it. That is, it becomes, well, we can expand it first to 3 to the power of 95 times 3 squared, mod 353, bring the mod in and so on, and expand it out. So it's 3, sorry? So he's got 40 as an answer. 40. Yeah. So the point is that some calculators will not handle such large calculations unless they can expand out the modulus. Simply calculating 3 to the 97 on your calculator will get a number that's normally too large for your calculator. So can we calculate? BC is a calculator on most Unix systems. It will calculate, let's try, 3 to the power of 97, if it calculates that, is a large number. And I'll copy that. Mod 353, 40. So this will calculate it. In other words, 3 to the power of 97 mod 353 is 40. So the answer is 40 in this case. That's the public value of user A. User B does the same, follows the same steps. They choose their own private value independently. They're on the other side of the world. 233 in this case. Can randomly choose a number within some range and calculates their value of YB. The same equation, alpha, the same alpha to the power of XB mod Q. Where alpha and Q are 3 and 353. 3 to the power of 233 mod 353. And again, we need our calculator. Three to the power of, let's see if it handles the full calculation. Slash means continue to the next line. So that's 3 to the power of 323. I'll do it all in one step. 248. Sorry, I'll move that across. So just a calculator to calculate these large exponentials. 3 to the power of 97 mod 353, 3 to the power of 233 mod 353 is 248. So they are the public values that the two users are going to exchange. They send a message across the internet to each other containing those values. B sends 248 and A sends YA equals 40. So that they both know those public values now. So continue. We both know alpha and Q. We have XA is A knows its own private value. YA is 40. YB is 248. So that's what's known by user A at the moment. If we go back to our algorithm, so that was those two steps were the key generation at each user. Now each user calculates a secret. K equals YB to the power of XA mod Q. YB equals 248. XA is 40 mod 353. (248) to the power of 40 is that mod 353, 162. Have I done something wrong? Who's following?
มีสูตรไหนผิดอ่ะ y ยกกำลัง
Wake up. There's a mistake. Find the mistake. XA is 97, not 40. So that's wrong there. It's 248 to the power of 97. YB, the Y value we receive, to the power of our private value. 248 to the power of 97, mod 353. That's the number. (248 to the power of 97 mod 353), 160. So know how many digits here? Well, this is maybe 60, 180. There may be 200 digits here. And we're using small numbers. Note that the values of X and Q that we're using are very small, too small. So in reality, for security, we use much larger numbers. And we'll be getting answers here which have hundreds, if not thousands of digits. And using the modular arithmetic as a way to efficiently perform that calculation. So that's performed at user A. User B does the same. User B has XB. XB is 233. YB, which they calculated, is 248. And YA, which they received from user A, is 40 in this case. Same calculation, take, back to our slides. User B takes YA, the value they received, to the power of their private value, mod Q. YA to the XB mod Q. Sorry. Mod Q is 353. And again, our calculator, we've got 40 to the power of 233 mod 353 is 160, but you knew that. That's our shared secret value, 160, the key. Both sides have k equals 160. We'll show you briefly why that's the case. It's some simple mathematics why they get the same value. And then we'll see why is it hard for an attacker to find that value. So they're the steps. Why did they get the same value? No, just simple high school mathematics. Maybe let's show our algorithm again and see what steps they did. User A selected or calculated a public value YA using alpha to the XA mod Q. User B calculated their value YB is alpha to the X. Sorry. They're the first two steps in their key generation. And we send that to B, that is we send YA to B, and B calculates K equals YA to the power of XB mod Q. Let's call this K KB. That is the key value calculated by B. The received YA to the power of XB mod Q. So let's expand that. That is, what is YA? Well, YA, if we put this equation or substitute for YA in here, KB equals, instead of YA, alpha to the power of XA mod Q, all to the power of XB, all mod Q. So all I've done is taken the equation for K at B's side and substituted in for YA. Alpha equals XA to the mod Q. And this exponential, we can bring what's alpha to the XA to the XB. It's alpha to the XA times XB, all mod Q. Just by simple expansion for that modular arithmetic. So alpha to the XA to the power of XB is alpha to the XA times XB. That's the value of K calculated by B. Let's look at it from A's perspective. A receives YB, and they calculate KA according to this equation equal to YB to the power of XA mod Q. Substitute for YB, that is, take alpha to the XB mod Q. All to the power of XA mod Q, and you get alpha to the XB times XA mod Q. And they are the same. That is, KA equals KB. It's just alpha to the XA mod Q. Alpha to the XA times XB mod Q. So that's why we get the same values of K. That is, they get the same secret value. Any questions on that before we look at the attacker? Each user generates their key independently using the public elements, the global public elements Q and alpha, known by everyone. Send their public values to each other, exchange them, and calculate their own value of the K, and they'll be the same values of K. That is a shared secret. Next step, let's see what the attacker can do to try to find the value of K. And we'll do it not through our example, but just through the equations. Ready for a surprise quiz at the end of the lecture?
No.
Why not? This is not so hard. This is not so hard, is it? Any problems? So we've just shown an example of the algorithm, and then we just showed there, why does it work? Why do we get the same K at both sides? Now we'll show, well, what can the attacker do? What's known? What's known by the attacker in this case? YA, YB, Q and alpha, and the algorithm. Q and alpha are public. By global public elements, Q is known. We had 353. Alpha is known, 3. And YA and YB are known. Those two values were sent across the internet. No secure channel, no encryption. The values were sent as they were. So the attacker, we'll assume, knows them. YA was 40. And YB was 248. And the attacker knows the algorithm. They know the steps that user A and B did. How do they solve and find K? Try. Try it. They've almost got everything, haven't they? So try and find K from those four values.
No, impossible.
What would you do? It's possible with these values. What equation would you write down? We don't know XA or XB, so let's not give up so quick. Let's see what we'd have to do. Some of the equations we know that they used, K, for example. We know this equation was used. We know YB. We know Q. We want to know K. We don't yet know XA. That's our first problem. How do we find XA?
We would force try.
Oh, we can be a bit more intelligent than that. Brute force is the last approach. But can we use the mathematics of this algorithm to write an equation that would find XA?
Use some Euler principle.
Well, how is XA related to the other values? Look at XA in this equation. We know that user A calculated YA from alpha to the XA mod Q. Now we're getting closer. We know alpha. We know Q. We know YA. Find XA. So we've got an equation with 4 variables. We want to find one of them. If we find XA, then we can find K. If we get XA, we've got it here, and we'll immediately calculate K. So the challenge, find XA. How do we do that? There's the exponential. We do a discrete logarithm. The discrete log in base alpha. So how to write this exponential as an inverse, it's a logarithm, where the base is alpha, mod Q of YA equals XA. So we simply need to solve the discrete logarithm. We know YA is 40, alpha is 3, Q is 253. With those numbers, you'll be able to get the answer. But if you choose large numbers, we already know with large numbers, discrete logarithms are too hard to break within reasonable time. So that's where the security comes in. The attacker needs to solve a discrete logarithm. Discrete logarithms are practically impossible to solve if we use large enough numbers. Since the attacker cannot find XA, then they will not be able to find K. And that's where the security of Diffie-Hellman comes in. Yeah, if you choose large numbers of X, XA and XB, then you see we also need a large prime number Q, because XA and XB need to be less than Q. So to be secure, choose a large Q, very large prime number. Sorry? Discrete logarithm. In modular arithmetic, when we talk about a logarithm, mod Q, we can call it a discrete logarithm. That's just the name. So D log. Discrete log. Discrete logarithm. It's a logarithm in modular arithmetic. It's just a logarithm, but mod something. Mod Q in our case. And we know that discrete logs are hard to solve. The way we read it, and the same as a normal logarithm, except we now have a base. Discrete log in base alpha, the base is alpha, because it's alpha raised to the power of something, comma Q, meaning in mod Q, of YA equals the exponent. That's how we read a logarithm. The log in base 10 of 100 equals 2, because 10 to the power of 2 equals 100. But now we have a logarithm. Modular arithmetic as well. So the result is that two entities in a public network can choose their values, exchange public values, anyone can intercept those values. Those two entities can calculate a secret key K, and no one else can find that K, so long as the values are large enough. So we've exchanged a secret key, which is a valuable service. Because if I want to encrypt something using DES, triple DES, AES, both of us need to know a key, the same secret key. We can use K, if we use large numbers, as our key. Just convert this into a 64-bit number or use it in some algorithm to convert to get a 64-bit number for DES.
So if other no only YA and YB of another person, know only that and the public Q and alpha.
Yes, the public values are known by everyone, and because we need to tell the other node the value of Y, someone can intercept that.
Yeah.
So the other person.
Can A send Y to B and B not send Y back to A?
No, they both need to know each other's value of Y so that they can calculate K. Because user A uses YB to calculate K, user B uses YA to calculate K.
So actually they want to send only 160, but in the form of YA and YB.
Yes, because if I choose secret key K equals 160 and send it to you, then someone can intercept that and find our secret key.
But okay, it's hard to find. If we want 161, maybe we have to calculate again.
No, it doesn't matter what value of the key is. If we use large numbers, we'll get a value of the key. I don't care what value of the key I get.
Don't care about
No.
the value of the key.
It's not like I choose 160 and try to send that to you. I choose a private value of XA and XB, send the Y values, and we calculate K. We don't care about the specific value here.
That guarantee that
Yeah.
the key must be the same, but
Key's the same, no one else knows.
that interface only know that YA and YB is enough.
Yeah.
Okay.
Yeah. Where do we use Diffie-Hellman key exchange?
Exchange key.
A more practical application. Yes, if we exchange keys, where do we exchange keys? You've done it before. Sorry? You've probably done it in Secure Shell. Most Secure Shell clients. Secure Shell we know is to connect to another computer, to remote log into another computer. And it's done securely. That is, when you send commands to that other computer, those commands are encrypted. So no one else can see the commands you're sending, and especially your password when you log in. All of those communications are encrypted. But how do you know the key to encrypt it? They use AES or a similar algorithm to encrypt. But how does your computer and the server computer choose a key? We don't want to use our password because we want to encrypt the password when we send it. So we need to choose a key that is known by my computer and the server computer. And they use Diffie-Hellman. They exchange the public values and calculate a key and then use that key to encrypt everything that they send. You can see that if you capture a secure shell exchange with TCP dump and Wireshark. You'll see the public values which are exchanged. This just shows the algorithm in the form of the exchanging the two values. We could do it. I could calculate in my head the value on a piece of paper, someone else could calculate, and we could yell out those values and it would still be effective. The YA and YB. It's secure from the perspective as to find K, you need to solve a discrete logarithm, but it's insecure against a man-in-the-middle attack. Not a meat in the middle, a man in the middle. Someone intercepts the messages in both directions and pretends to be someone else.
Algorithm user A send first, and then the user B calculate and send.
Yes, they need to exchange these two values. That is, one, they need at least two messages to be sent. You'll see when, for example, when it's used in secure shell, those values are included in other messages as well. That is, when you start up the connection, you can exchange those values. You can choose the values of, the Q and alpha.
And then after this, they have the same key and start communicating.
Yeah. After this, A can encrypt using the key K, and B will be able to decrypt that using AES, DES, triple DES, whichever, even RSA. It's insecure in that someone in the middle can pretend to be one of them and discover the keys. The way to make that secure is to use further authentication, digital signatures and certificates, which we'll go through in the next topic, or in the next topics. There are other public key crypto systems, RSA, Diffie-Hellman, and there are others. Elgamal, elliptic curve, and there are even others than that. But those two are perhaps the most commonly used that we will see. Any questions on Diffie-Hellman? Try the example. Make sure you know why it works. Make sure you know why both sides get the same value of K. And make sure you know the steps that an attacker would take to try and find K, and why it's practically impossible if we use large enough numbers. Countermeasures are measures to prevent the attack, to stop the attack. Yeah. There are possibilities of a man-in-the-middle attack. There are ways to stop that using other authentication techniques. Man in the middle is someone pretending to be one of the others. Yeah, you can stop such an attack. So it's still useful, and that's why it's still used with a secure shell.
Why man in the middle can attack this?
Try it. That's a good quiz or exam question. See what happens if you have someone in between A and B that intercepts both messages and pretends to be, or pretends to be both of them. Any other questions? That's okay.
I understand.